All right, so this is the last property that we are going to, let me make sure this is right what I'm saying. The last property that we're going to learn how to determine about a function. Okay, and then we're going to apply it to other kinds of functions moving forward. So obviously we're doing other new stuff, but this is it. When we talk about, like in MHF, that a function is increasing, and now we're using the derivative to determine when it's increasing. This is another one of those kinds of things, and it's kind of the last one. So today we're learning about it. We are going to do a sketch today and do a couple other questions about it. And then tomorrow, a couple more sketches talking about it and just practicing, and that kind of sums up the unit. And it is concavity. This is something you probably, especially if you've taken, I think it's in physics, right? You talk about concave versus convex, which is not what we do, not quite. We look at two things, which is this, concave up, and like this, which is concave down. So I think that's intuitive, but it's something you definitely need to know. You don't want to get those backwards. So concave up, this is called the second derivative, which we haven't done that yet, but I'm going to write this down now. When the second derivative is greater than 0 or positive. And concave down, our second derivative will be less than 0. And so it's very similar to a function is increasing if the first derivative is positive, and decreasing if the if the first derivative is negative. It's concave up if the second derivative is positive, and it's concave down if the second derivative is negative. So it's the same kind of thinking, but it's telling us something different from increasing versus decreasing. And then the last thing here, a point of inflection, which we will shorten to POI, is where concavity changes. So those are just the facts. How do we use them? First, we're going to do a little bit of practice, because some people are very visual and will just do this automatically and easily and just get it. But some people aren't as visual and have to spend some time sort of thinking and coming to terms with whether a graph is concave up or concave down. Some people might confuse it a little bit with increasing, decreasing. As I'm sure many of you have confused increasing, decreasing of the function with positive, negative in the first derivative. This is just one more layer on the whole situation that we also have to make sure we connect with and understand. Okay, so for every one of these points, I'm going to do a little table here. Looks like a derivative chart. It's not exactly, but it's sort of purposefully set up to be similar to that. So for point A, on this diagram, do you think the function at point A is concave up or concave down?
Concave down.
Concave down, very good. So I'm going to do this, concave down, CD for concave down. Sorry, I put that in the wrong column. So F double prime will be what? Yeah, negative. And concave down, I should put it in that. What about point B? Yeah.
Concave up.
Concave up. So the second derivative is positive. Which means, everybody look, somewhere in here is a POI where it's changing from concave down to concave up. It can be very difficult to pinpoint exactly where that is. And that's not something you have to be able to do. You are going to label those points on graphs. And if it's way off and kind of is like glaringly wrong, you could lose marks. But generally, if you put it in there somewhere, like I would just kind of stick it right around there, that's good enough. But it's hard to tell exactly where it is. But you can narrow it down to hopefully a small range. Okay, what about C?
Is this a graph of the second derivative?
No, this is this is just a function. Is this function at point C concave up or concave down? Concave down. Which means the second derivative would be negative. And what about D?
Concave up. Down.
Think down? What do other people think?
I think up.
Thinking up?
Down.
Vote for another vote for down. We're going to have a class vote here. It's concave down. So this is what I'm saying. It's not as easy as we might think. But point D is still concave down. And in fact, I'm going to stop right now, and I'm going to go back up here, and I'm just going to point something out that I want you to think about over the next couple of days, and I guess over the break, is if I have an asymptote, and my function is approaching that asymptote like this from above, is the function concave up or concave down approaching that asymptote? It's hard, isn't it? Up is correct. This is concave up. But it can be tricky or confusing, in particular until you, I suppose, get more used to the idea. And then if I'm approaching that one's concave down. So it's increasing forever, but concave down forever going out that direction. That almost seems counterintuitive. But that's what happens around horizontal asymptotes. Okay? And that's something that you've got to figure out for yourself, kind of thing that you got to get used to. Okay. Next one. E, F, G. So point E would be concave up or concave down?
Down.
Concave down, very good. So second derivative is negative. F?
Up.
Down. Point F is still down. But what about point G? That one is up. So again, somewhere in here, it's changing from up to down. From down to up, I should say. Please?
Sorry, how is that down?
Because it's curving down. It's still curving down, and then somewhere in there is when it starts curving the other way. Or maybe it's even closer to F. Maybe it's like right around there somewhere. Think of concavity as like, if you kept going, would you end up pointing down or not? And to me, at F, it's still curving downwards. But then it changes with a point of inflection and starts curving up. Like if you kept following that around, you'd end up pointing up. Now the function doesn't do that, but you can think about it that way. It's like, which way is it swinging around? This here? Because that's the relationship. So whatever this function would be, its second derivative would have to be negative because the function's concave down. Now we're going to use that in the other direction. We're going to determine whether the second derivative is positive or negative and use that to determine that, okay, it's negative, so our function must be concave down, right? So we're going to use it the other way, but that's the connection between the second derivative and concavity, just like the relationship between the first derivative and increasing, decreasing of a function, right? If the first derivative is negative, the function is decreasing.
So then wouldn't it be fairly easy to find quantity functions? Like wouldn't it just be where the second derivative is 0?
Just like we do the first derivative is 0 to find critical values, right? Exactly, yeah. So we'll do an example of that if not everybody's quite there yet. Any other questions about this? Take a look here. This might help. I'm not going to take up too much time doing this because we have 3 examples that we want to get to. Here's the first derivative on top. Here's the original function on top. Here's the first derivative. Okay? And watch what I'm going to do. So I'm going to drag this, and the function is increasing, and the first derivative is positive. This is what we already know. This is not new. Okay? Then the function switches to decreasing, and the first derivative is now negative. Then the first derivative goes to positive, and we notice that that is where the function is increasing. And we already know x-intercepts of the first derivative line up to turning points or other things, critical points, in the original function, right? That's what we already know. Here's the second derivative. Look what happens. This is concave down, isn't it? All here is concave down. Until I get to this point where now I'm positive in the second derivative, and now this function is concave up. There happened to be a point of inflection that looks like it's an x-intercept of the original function, but that's just a coincidence. Let's look at a couple others. Okay, so this is concave down, so the function is negative. And notice that the dot changes color. I don't know if that helps. And then when the second derivative is positive, this function is now concave up. Can you see that? What's going on with this one? Can anybody explain it?
It's always concave up.
Yeah, it's a parabola. It's always concave up. I mean, it looks like the example we drew at the very start. So this is a constant and always positive. If you had a parabola that was opening downwards and concave down, your constant would be in the negatives. And we can make sense of this with our understanding of derivatives, because if I take the derivative of the parabola, I'll get a degree 1 function. If I take its derivative again, I'll get a degree 0 function, which is a constant. So even algebraically, that's something that we should be able to make sense of. What's happening with this one? I'm concave down, and then I switch to concave up. Interesting that those graphs look a lot alike. But if I switch to the first derivative, this original function, the green one, is always decreasing. So the first derivative is always negative. But if I switch, but the concavity is changing. And then there's a few others. Maybe we'll look at these more tomorrow. I think I'm going to stop there. So this is, we'll do one more. This is concave up. So this is positive. Now it's concave down. Now the function goes above the x-axis, but that's not relevant, right? And so this is always negative. The second derivative is always negative in this section because that part's concave down. And now I'm concave up again. So the second derivative is positive again. Any questions so far? Okay, so there's a couple of different kind of questions that we're going to do using the second derivative. I don't know if this is obvious. I haven't actually said this yet, not today at least. What even is the second derivative? To many of you, maybe it's obvious, but Yeah, so you take the derivative of the function once to get the first derivative, take the derivative again to get the second derivative. Could you have a third derivative? Of course, you could take the derivative as many times as you want. But the third derivative doesn't tell us anything about the function. So that doesn't help. Could it tell us something in real life? Yes, possibly, when it's applying to some specific situation. But generally, the second derivative is as far as we take it. So question, example 1 here says, find the critical points for each of the following functions that are going to be below. Use the second derivative test to decide if the point is a local max, a local min, or neither. This is important because when we do sketching from now on, we will no longer be doing a first derivative chart. And a first derivative, unless you're told to sketch with just the first derivative. The first derivative chart is how we determine whether something was a turning point max, turning point min, cusp max, cusp min, whatever, right? That's how we were doing it. We were looking at the intervals of increase and decrease and whether the derivative was 0 or does not exist. Everybody following me okay on this? You know what I'm talking about? We did these kinds of questions. And in the first derivative chart, in that chart we've been building, we slot in and classify the points. But if we don't have a first derivative chart, how do we classify the points as maxes or mins or whether they're turning points or cusps or that kind of thing? So we need to be able to use the second derivative to determine if a particular point, critical point, what it is, to be able to classify it. Okay. So first one's just a polynomial. First thing I'm going to do is take its derivative. And I have to find the critical values to be able to classify critical points. So I am going to factor this. Okay, done. Next thing, find the second derivative. Second derivative is y with 2 tick marks, just like I did f with 2 tick marks in the last one. Take the derivative of the derivative 6x minus 18. Factor that as well. Okay, no big deal, right? Polynomials, pretty straightforward. Taking the derivative again. Everybody okay? Okay, 4, critical values. Critical values occur when the derivative does not exist or when it's equal to 0. Well, the derivative, first derivative, exists for all x. Y prime equals 0 when x is 2 and 4. That's all stuff we've already done. I mean, taking the second derivative we haven't done, but it's no different than just taking a derivative of an expression. So far, hopefully, so good. Now, what does our test look like? Second derivative test. So I'm going to take those x values, sub them into the second derivative, and see what I get. So what? How do we interpret this? So I found my critical values. I subbed them into the second derivative. Nasir, what do you think?
So since it's a negative value, x equals 2, that means that it's going to be concave down.
Very good. The second derivative is negative in that location, so the function is concave down. But I'm supposed to be classifying the point. What are the different things that a point could be? A point could be a turning point max, turning point min, cusp max, cusp min, although that's when the derivative does not exist, which didn't happen in this case. Or it could be a horizontal twist, or it could be a vertical twist. So which one of those things is this? Why? If it's concave down, it's doing this. So it doesn't have to be a max. Right? That's how we use the second derivative to determine and classify what a critical point is. Therefore, turning point max, I know it's a turning point, and I'm subbing my value into the original function to get the y value of 10. I know it's not a cusp because that's where the derivative does not exist. So we know it has to be a turning point. And this one was positive 6, therefore concave up. Therefore, turning point with a min and subbing the critical value of 4 back into the original function. You can do this if you want. I'm just going to state it to save some time. So I'm putting it back into that, and I get a y value of 6. This is concave up region, so I've got a minimum. Again, if you want to draw it out so that you can think of what it is, then go for it. Scrap paper off to the side, whatever you need. Make sure you can do this part correct. We do see people making this mistake on tests. What do you think? Is it okay? Okay, one more of this same type where we're just classifying critical points using the second derivative test. Then we're going to do a sketch.
So what would be the value of the second derivative also not exist if there's like a cusp max at that value?
So if when you're taking the second derivative, you're taking the derivative of the first derivative. If the first derivative doesn't exist there, you're right, the second derivative will not exist there as well.
How do you know if it's like a cusp max or a cusp?
Well, you will know that the original function did exist, the derivative does not exist, and you would still be able to think about whether concavity is changing or not, because that will tell you what's happening. So we'll look at some of the, I'm not going to go into it right now because I want to get these two examples done, but we will look at that, okay? And if you start drawing it out, and especially after you've worked with concavity for a day or two, and you draw them out, you would be able to figure it out. I mean, just imagine cusp, concave up and concave up. Doesn't change. Okay. So I'm going to take the derivative. So this is equal to 20 x squared plus 4 to the negative 1, right? So f prime at x is negative 20 times 2x, the derivative of what's inside, times x squared plus 4 to the negative 2, which is negative 40x over x squared plus 4 squared. What do I need to be careful of for the second derivative? Sarah? Yes, and because I did that here as well, right? The 2x, but quotient rule. That's enough to trip some people up because we just did it. We did the first one without quotient rule because it's not quotient rule. It's a constant on top. But now there's an x on top. Now it's quotient rule. And only because we did it this way the first time, we're going to think our brain's going to go there and try to do it that way the second time. But this is quotient rule. So this is the derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. So we got to clean this up. So I'm going to factor out the negative 40 and an x squared plus 4. And I'm left with x squared plus 4. Let me know if I'm going too fast. Minus. What am I left with here? I'm left with this 2. Whoops, what happened? I'm left with this 2x, and I'm left with this x. So, minus 3x squared. 4x squared, sorry. X squared plus 4 divides with 1 on the bottom. And I get negative 40. And then negative 3x squared plus 4. Any questions? Again, we've done a lot of practicing taking derivatives. It's no different just doing it twice. The second derivative is often a bit harder or can be a bit harder because it ends up being quotient rule or whatever. You got to make sure you clean up the first derivative properly. We'll talk more about this tomorrow. Not only clean it up properly, but which form of the first derivative is easier to take the derivative of. In some cases, you're going to have to decide that. Take the derivative again. When you're doing a full sketch, factor it, clean it all up, simplify it, do a whole bit, right? So you're doing it twice. Okay, critical values. And then the other thing in particular about sketching is whenever you're finding critical values or finding intervals of concavity or intervals of increase and decrease or points of inflection, all these different things that we're going to find, which version of this thing am I using? Is it the original function? Is it the first derivative? Is it the second derivative? Right? And you've got to be comfortable making that choice and knowing which one you're supposed to be using. So for critical values, that's what we've been doing all along. It's just the first derivative first derivative does not, oh wait, I was going to say it's got an asymptote. It doesn't, does it? Why? If it was x squared minus 4, it'd be different, but...
Can't be a negative on the bottom.
Yeah, you can't get, when you're squaring something and then adding to it, you're never going to have 0, you're never going to have negatives. So f prime at x exists for all x. And it equals 0 when x equals 0. How do I know? Looking at the first derivative. Okay. Now we'll do our test. I sub the critical value into the second derivative. I suppose in this case, I didn't have to simplify. I could have left it like this and just subbed into that. But to me, it's worth it. This is a lot easier. And for sketching, that's what we're going to have to do anyway. This looks like negative 40 times 4, which is negative 160, over 4 cubed, which is 64. But like we talked about, all we really care about is that it's negative. You don't have to even evaluate it. I don't need to see that. You can just do it by inspection if you've got the factored form and say equal to negative, as long as you do it correctly, right? Therefore, second derivative is negative, so it's concave down. So it's got a turning point, max at 0. Subbing 0 into the first derivative, or sorry, not first derivative, the original function, the first function that we had there. Looks like 20 over 4, which is 5. Okay, any questions before we move on to our sketch? Everybody's okay? Or you've given up? Which one is it? Okay. Sketch the curve below showing all points of inflection and everything else. Intervals of concavity, increase, decrease, critical points, intercepts, asymptotes. I didn't write it all down, but I said this the other day. Sketches always include all those things. And now they also will almost always include points of inflection as well. This is the whole show. This is everything we've got. We're not adding anything else. So if you can do this, you can do it all, I guess. Okay, so first thing I'm going to do is factor this thing. And if you want, you can expand the bottom. This will be a good example of why we might want the bottom expanded, but it's entirely up to you whether you want to bother or not. You don't have to do that, so you don't have to show me that, but you got to get the values right later. So if it helps you get all the properties of the function correct, then it's worth doing. Then I'm going to take the derivative. And this is quotient rule, and this is what I was talking about. So which one of these things do I want to take the derivative of? Which of the three lines? Right? But usually we just go with the first one. This one up here. So, derivative of the top is negative 2x times the bottom minus derivative of the bottom, which is 2x plus 2 times the top over the bottom squared. Factor out a negative 2. Factor out an x plus 2. And I get x times x plus 2 minus 9 minus x squared. And x plus 2 is going to cancel. Whoops, I made a mistake. I'll show you in a second. Is everybody okay so far? I factored out this negative, so this should be positive. Okay, careful. I factored out that negative. Which means this x squared is negative x squared. Which means this is just 2x minus 9. Mm-hmm.
Isn't it plus 9?
Plus 9, yep. Thank you. So that's just the first derivative. You okay?
Shouldn't it be a 3?
What?
Like above the last step. The x in the denominator.
Yeah. Okay, now we do it all again. Second derivative. That negative 2 on top is going to be a bit of a pain. You can take the derivative with it if you want, but I can also factor it out and use constant of a function rule and just leave it out and not use it in derivative. Do the whole derivative in square brackets, and then the negative 2 will join back up inside later. You do it how you like, but I'll show you this trick in case you want to use it. So because I have this constant out here, I can actually just leave it outside the whole thing. Try it this way and try it another way by keeping the negative 2 in there. It's just going to factor out later anyway, so you're going to get the same answer. But, and you decide which one you like better. You could also, yep, very good, expand the negative 2 into the brackets and do it that way. Then you'd end up with having to factor it back out, possibly later at least, but then you just do that, right? Yep, good. Okay, so derivative of the top. Now it looks like 2. Because I'm only taking the derivative of that bracket times the bottom minus derivative of the bottom times the top over the bottom squared, which is x plus 2 all to the 6th. So all I can factor out is x plus 2 squared. I'll apply that negative back in, that negative 2. The x plus 2's divide. And I get x plus 2 to the 4th. And you remember when we first started doing this, how I told you that the denominator will always be like increasing by a power. So you see this when you take the derivative twice. It started as x plus 2 squared. Next one was x plus 2 cubed. Next one is x plus 2 to the 4th. Right? After you've fully simplified, you're going to see that happening in these rational functions. So it's a good check that you're on the right track. Let's see. 2x minus 6x is negative 4x. And 4 minus 27 is negative 23. And I'm going to factor the negative out of that bracket and cancel it with the negative in front of the 2. And there's the simplified version. Man, it's hard to imagine, after all of that algebra, taking the derivative twice, that you get something that cleans up so nicely. Yeah?
So, what's the point of taking the second derivative in this question?
So we can find points of inflection. Well, we talked about that at the beginning. We're going to do it, so if you still have a question about it after, then you can ask then, but why don't you wait till we see? Because the instructions say find the points of inflection. You're not going to find them without the second derivative. Any other questions before we move on? Okay, so we're starting with intercepts. Oops. Now let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different lines. Which one are we going to use to find the y-intercept? Which one are we going to use to find the x-intercepts? Right? And I think in a lot of cases it's going to be clear and straightforward and obvious. You're used to doing this, but it is something that people mess up or start to overthink and confuse themselves. So keep that in mind. So what do you think? I'm going to use the original function to find the intercepts.
Oh, I thought that's what you were asking.
Yeah, okay, so original function.
The expanded version you would use for the y-intercept.
Yeah, very good. That's why I expanded it, right? This one's the expanded version. Sub 0 in for all the x's, they're all gone, and I get 9 over 4. X-intercept. Again, using the original function, it's going to be
Positive or negative 3.
plus minus 3, very nice. I'm using the factored version for that. Okay. Asymptotes. Vertical asymptote.
X equals negative 2.
X equals negative 2. So factored bottom of the original function. And we'll do our testing. Limit as x approaches -2 from the left of y. Limit as x approaches -2 from the right of y. So putting numbers just to the left of -2 and just to the right of -2. But this bottom's always positive because it's quantity squared. So whether inside the brackets is positive or negative, you're squaring it. And if I'm putting something negative in these, what am I getting? Three plus -2.01 is still positive. 3 minus -2.01 is 3 plus 2.0, so it's still positive. So that little backwards thing of the 3 minus x instead of x minus 3 can be tricky. And you can factor out the negative if you think it makes it easier. Where am I here? But this is going to be positive infinity, and so is this. Don't take for granted all of that testing. It's similar to what we did in MHF, but because of all the extra stuff that we're doing, you can start to confuse yourself what you're punching it into. So people can make mistakes doing that. So make sure you're doing the practice and that you can do that yourself. This is not an oblique asymptote, it's a horizontal asymptote, and the horizontal asymptote is this here? Yeah, y equals -1. From expanded version, it's -x squared over positive x squared, so -1 over 1, which is -1. I didn't do this before, so I'm going to do it now, just so I can use this notation. And I get negative, so I'm punching this into my calculator, right? Again, coming back up here and deciding which one is easiest to plug into. For horizontal asymptote, you need the value. We're not doing it by inspection. So this one was -1.04. This one's -0.96, I believe. So this one's below, and this one's above. Oh my gosh, imagine doing all of this, taking all those derivatives, doing all of that incredible work, it's all amazing, and then getting those backwards because of the negative, and thinking that -1.04 is above -1. But that's what happens. You're focusing on other harder things, all the new stuff, and then you muck that up. Whoops. And that's not going to match your intervals of concavity and increasing and decreasing. So that's going to cause an issue. You're not going to be able to draw a graph that makes sense if you make that mistake. So sometimes every tiny little bit counts. Okay, everybody good so far? Yep.
Will you give us a second derivative on it?
Yes, but we may not, every single question we're not going to give you all the derivatives probably. So there will be a time where you're going to have to take the derivatives yourself on a test. Whether it's a full sketch or we're just going to say do a first derivative chart or something like that, you'll have to do it, yeah.
So now we're doing Wednesday and Thursday. Is this what we're doing Wednesday? Half an hour?
Let's talk about that after, okay? Let's get this done. So now I do my critical values. Y prime does not exist when x equals -2. Looking at the first derivative, the denominator is 0, so the derivative does not exist at -2. But that's a vertical asymptote. We've already done the testing for it. So there's no critical point there. Where does y prime equal 0? Again, you got to go and pick. which of those 12 lines you're getting this from. The first derivative, when the top is 0. That looks like negative 9 over 2. Which is negative 4.5. You may want those decimal values. All right. So that's done. We found our critical values. Now for what is that? Points of inflection. Why did I write 2 P's? What do you think? What's your guess? No? There's a strange thing about points of inflection that when we go and find them, we're going to find a value. Sometimes it's not a point of inflection. Sometimes it's just nothing. So for now, we're going to call them possible points of inflection. That's what the second P stands for. We're going to find some values that are possibly points of inflection. Then we're going to do some testing to see if they actually are. Okay? How do we find where the point of inflection is? Jack already told us.
Sub it into the second derivative.
We're not. Sub what in?
4.5, negative 4.5.
No. Good idea, but no.
And the second derivative equals 0.
When the second derivative equals 0. If the second derivative is positive, you're concave up. If the second derivative is negative, you're concave down. What happens if the second derivative is 0? It's not concave up or concave down, so it's in between the two. Right? So for possible points of inflection, it's your second derivative does not exist or equals 0. So y double prime does not exist at x equals negative 2, but again, that's a vertical asymptote. Y prime equals 0 at negative 23 over 4. I got to speed up here because we're going to run out of time, which is negative 5.75. Okay. Now what we're doing is called a second derivative chart. When you have to find points of inflection, you don't do both charts. You don't need a first derivative chart. We only need a second derivative chart. So I'm looking at starting with negative 5.75. That's the furthest to the left. So x less than negative 23 over 4. Negative 23 over 4. Negative 23 over 4 less than x less than negative 2. We still need our asymptotes in there. Negative 2 and x greater than negative 2. Mm-hmm.
You use the asymptote in the second derivative, right?
Yeah. Yeah, we got to have the asymptote in there as well, because concavity can change at an asymptote, just like increasing, decreasing can. Okay, so I'm subbing a value in that interval into the second derivative. So I'm going way up here and subbing something big negative into this, so like negative 100, and it's going to work out to be negative. This is the same kind of testing that we've been doing, exactly the same, but now we're doing it in the second derivative. So I've got negative, then I've got 0, then I've got positive, then I've got does not exist, then I've got positive again. So this is concave down. This changed from concave down to concave up. So that is a POI. This is a vertical asymptote. And this is just concave up. Last thing we have to do, hopefully we can fit this in. Where is my critical value? Go find it. Negative 4.5. What interval is it in? Like, here's the thing. I'm going to do this for us right now, but you're going to have to be able to do this. It's fussy work sometimes. You got to look at the decimal and just think about, well, where is it relative to the others? It's in here. Okay? So if I've got a point in a concave up region, I've got a turning point with a min, because it's concave up. And this point is at negative 9/2, negative 1.8. I'm graphing this, even though we're going to run out of time. I don't care. So I've got, but maybe you want to watch instead of trying to keep up and get it copied down later. I've got that there, and I've got this here. Okay, and I've got a y-intercept of 9/4. I got an x-intercept of 3. This is x equals negative 2. This is y equals negative 1. Here are my behaviors. Going up, approaching from below, approaching from above. So watch what happens. I come down. Oh, and I got an intercept here. Get rid of that. Okay, and this point is this, B. Okay, hold on. And where's point A? Negative 23/4 was our negative 5.75. So that's over here somewhere. I want to do this again. So, now I'm rushing. Okay, so I go like this. And somewhere in here it changes from concave up to concave down, and it looks to me like it's right about there. So that's my point A, my point of inflection. You were asking before what a point of inflection is. There it is. So without our second derivative chart, I wouldn't be able to find that point and do that. Hold on, one more thing. And notice how this is concave down as I approach the asymptote from below. Okay, you get the idea. Okay, so there's that function, and we'll do a couple more of those tomorrow.